Good morning, ladies and gentlemen. Today is our final video for thermodynamics, and we are going to talk about the second law of thermodynamics and its relationship with heat engines. The second law of thermodynamics basically has a few points to it. The first point being that heat will spontaneously flow from a higher temperature to a lower temperature, and it cannot happen in reverse. And the more important thing actually is that some of the work, some of the heat flow, or Q, can be converted into useful work, but not 100% of it. Okay. So if we think about that in relationship with our heat engine, and that's our diagram on the right, basically, we start with a higher temperature and a lower temperature, hot and cold. Heat will always flow spontaneously from the higher temperature to the lower temperature. But as the heat is being taken out, we can use up some of that energy within our engine and turn that into useful work. And whatever energy is left over gets deposited in the cold reservoir. So if we were to look at our steam engine, our basic idea of how a steam engine works, you have our hot on top, we have our cold on the bottom. The energy is used to boil the water, and which then turns to steam. The steam flows through the system. Some of that energy of the steam is being used to, whether it could be used to run a piston, as it shows here. It could be used to turn a turbine, whatever it's used for. And the energy that's left over will then, goes into the bottom. It condenses, it turns back into water, which then gets pumped back up inside. So we have our QH over here as it flows down. Our work is being generated, and we have a QC, that's the energy that's left over going into the cold. Okay, so this is just a basic representation of what a heat engine does. Understand, however, that 99% of the power that is generated in the world today is based on this simple steam engine diagram. Whenever you talk about coal, or oil, or natural gases, even if you talk about geothermal plants, or you talk about, whenever you're talking about energy, our generators all run on the basic idea of boiling water, turning it into steam, turning that giant turbine to make electricity for our homes. Okay, so it's a very, very simple idea. There's one other part to the second law of thermodynamics that I'll mention briefly here, but we're not going to get to it too much. And the third idea is about the idea of entropy, which basically means a state of randomness. And the second law also basically states that all natural processes tend to increase in entropy, which is represented by the letter S. In fact, if you were to give a formula for entropy, the change in entropy of any system is simply a function of its heat divided by its temperature. But really, it's directly related to heat. If heat is being added into the system, there's more entropy. If heat is being taken out of the system, there's less entropy. So positive Q equals more entropy. Negative Q is equal to less entropy. Okay? But it's a statement that we'll look at more later on when we do some AP questions. What is a heat engine? So as we said before, a heat engine is basically any device that turns thermal energy into useful work. And when I say what does work mean exactly, then usually it's the most easiest idea is just the one idea of a piston. Okay, so when we look at the steam engine, it's literally applying a force over distance, so the energy is being used up by the engine. Now, what I would like to point out, however, is that in terms of energy, we have QH is the total energy going in. So that means that QH is equal to some work that's being done and whatever energy is being left over. Okay, this is the leftover energy. So really I could say that work is equal to QH minus QC. Okay, the difference in energy, the difference in heat energy is equal to the amount of work that's actually being done. Okay. A combustion engine works on the exact same principle, where we have heat being added in from gasoline explosion. Here, let's actually take a look at an animated picture over here. So we have right now a piston that is just being ready to go. What initially happens is we have a gasoline mixture that's injected into the system. So I'll pause it right here. So this part over here, normally your fuel injection system will inject a few droplets of gasoline. Your spark plug takes that gasoline, ignites it, causing it to explode. So at this point, we have our creation of our QH. Okay, that heat being added in eventually gets all used up. And after it's used up, then the piston will come back down, and any sort of leftover waste from the gas gets expelled outward, and that goes out your exhaust system. So QC goes out. So the work that was done is the work done in moving the piston up and down. We had the QH that was originally being added into the system through the fuel injection system, and our total work can simply be measured in this chart over here. Okay, and we'll take a look at this chart again when we talk about engines more closely. Okay, if we were to graph what that engine did on this diagram over here, okay, so initially from A to B, we have the fuel injection system. Sorry. Insert gasoline, which is ignited by the spark plug, okay, which causes the piston to expand outward. That energy is used up, right, and we generate all this work as the piston is expanding out. But afterwards, they want to get rid of the waste product. So by pumping out the waste product, you're going to decrease the volume within the piston itself. So over here is where the leftover waste is pumped out. And the piston is brought back to its original state. If this is the diagram of a heat engine, if we were to talk about what a refrigeration system looks like, it would be the exact opposite. Now, before I start this video, before we had a picture of our high temperature and our low temperature, our cold. Okay, and of course, there's the engine in between. So a refrigeration system does the exact opposite of what a heat engine does. What it actually ends up doing, it draws the heat out of the inside of the refrigerator. The engine puts in a whole bunch of work to force that heat that it just took through these cooling panels, and that heat is then given off to the outside system. So any system that gives off heat is really a refrigeration system because it's taking the heat from the inside and depositing it on the outside. And this video does a nice job of explaining that.
Picture of what's going on in the refrigerator, and I'm basically showing you some tubing, metal tubing, aluminum tubing, some kind of metal tubing, and a couple of devices, a compressor and an expansion valve. Let's just see how this thing works. So the working fluid is sometimes a gas, and I've designated that by red, and sometimes a liquid, and I've designated that by blue. So what happens? Well, there's a compressor. The compressor is a pump that pressurizes the working fluid and pumps it around in this loop. And so when the compressor gets a hold of the working fluid, it compresses it, and it becomes a high-pressure gas. And then...
Okay. Now, to just take this quickly, so we end up with QL over here. Okay. This is the inside of the refrigerator, and it literally takes the energy out, absorbs it in. Work is done by the compressor to create a high pressure gas. So therefore that high pressure gas, like QH, will then want to leak out into the surrounding atmosphere, which is why if you think of a refrigerator, how there's always all this heat coming out from the bottom of the refrigerator, that's literally because you have these expansion coils which are giving off that QH. So let's watch the rest of this video.
That fluid moves through some coils, sometimes in the bottom of the refrigerator, which is actually a rather poor place for it energy efficiency-wise. Better places on top, and you may have seen ancient refrigerators that actually have a little round thing on top, and that was a better place to put these coils. Sometimes in the back, sometimes they're in the bottom. But the purpose of those coils is to take that high-pressure gas and let it get rid of some of its energy, in the process condensing to a liquid. So as it goes through those coils, it gets rid of some of its energy. It rejects that energy to the outside environment, the room the refrigerator is in. Translation, if you touch the coils of the refrigerator, either underneath or in back, they're warm. They're giving heat out to the room that the refrigerator is in. A refrigerator, ironically, gives off heat. Well, not so ironically. We'll see why in a minute. Okay, so now we have the working fluid in liquid form, but it's still at high pressure. It's rejected this heat to the surrounding environment. Then it moves through the expansion valve, and the high-pressure liquid going through this valve, which is basically just a tiny hole in a tiny little orifice where the gas is forced to go through, and as it goes through, it expands and cools and becomes a low-pressure liquid. So now we have low-pressure liquid, and the low-pressure liquid is then circulated through a series of coils that are insulated from the outside environment, but they're in contact with the innards of the refrigerator. And heat flows. Again, that's the right term because heat is energy flowing because of a temperature difference. Heat flows into these cool coils, and it evaporates the liquid, and it takes energy to evaporate the liquid, and that energy is ultimately extracted from the materials inside the refrigerator. It goes into the working fluid. It's pumped around. The heat has been extracted from the contents of the refrigerator, and now the working fluid is a gas because it's evaporated at the expense of the energy of the things inside the refrigerator, and it goes back to the compressor, and the cycle starts over again. The net.
Now, the fact is that most of our problems are actually going to be about heat engines themselves. So if we were to talk about determining the efficiency of any sort of heat engine, then it's really going to be a ratio of the work done versus the energy required. So formula-wise, if I were to say what efficiency really was, then efficiency is just equal to work over the heat input, absolute value. And efficiency, of course, is going to be a percentage answer, meaning that if you put in, for example, let's say 1,000 joules of energy, but only 500 joules of it was managed to turn into useful work, then of course, therefore, you would end up with 50% efficiency, or 0.5. Now, the thing is, we also have another point for work we could replace this with, simply because we had redefined work as the difference between the heat energy input and the heat energy output. So we could also write this as QH minus QC over QH. Okay? Which, of course, could then be rewritten as 1 minus QC over QH. So there's a lot of different variations of this formula, but ultimately it's just about how much work was actually done versus the amount of energy that was put in. And this is about the efficiency of a heat engine. Okay? Now for a refrigeration system, which has a completely different formula entirely. Now if I were to do a quick example with this, okay, an automobile has an efficiency of 20%. That means efficiency is equal to 0.2 and produces an average of 23,000 joules of work per second. So work is equal to 23,000 joules, but they say per second, and we'll talk more about what that really means and how we can rewrite the formula because of that. But it's 23,000 joules of work per second during the operation. How much heat is discharged from the engine per second? So looking for QC. Of course, that's per second also. Now, if you know efficiency, you know work, you can, of course, solve for QH. Efficiency is equal to work over QH. And right now, the smartboard is acting a little bit slow. So let's just pause this right now. Okay, so we know that efficiency is equal to work over QH. So QH is really equal to the 23,000 joules divided by 0.2, which is equal to 115,000 joules. And since work is equal to the difference between the heat input and the heat output, then QC is simply equal to the QH minus work, excuse me, which is equal to 115,000 joules minus 23,000, which is equal to 92,000 joules. Okay. Now, at this moment, I'm going to take this time just to rewrite the formula again a little bit because I want to incorporate the per second. Because whenever I talk about work per second, that's just a fancy way of saying power. Because power was work is equal to work over time. So what I could have written also was efficiency is equal to work over QH, but it's also equal to work over time divided by QH over T. So when we talk about work per second versus heat input per second, sometimes rather than using work over time, they're going to simply write that as the power done. And when we do some AP questions later, we'll see how it can be substituted in. But it still ends up being the same exact formula. Okay. Carnot was a French scientist who was thinking about what ways could we use to make this heat engine more efficient. And he came up with the idea of ideal efficiency, meaning that as the piston expanded and compressed, what if we were able to neglect any sort of friction inside or neglect any sort of turbulence within the gas inside? How could we make this as ideal a system as possible? And you realize that if you take the cycle slowly, okay, if you take the heat engine cycle slowly, you end up with specific scenarios for each phase. And you realize that it starts with an isothermal expansion, and then an adiabatic expansion, then an isothermal compression, and an adiabatic compression. Okay? So if I were to just rewrite that out, adiabatic expansion, then an isothermal compression, and an adiabatic compression. Okay, if you start with those 4 steps, okay, let's go to our example over here. Okay, over here we have our Carnot engine again. So that means when heat was first being input into the scenario over here, this is considered an isothermal expansion, meaning that as it's expanding this way, we have negative work. And I know it says positive over here, but it's really a negative value. And in terms of delta U, which is what DE stands for, delta energy, delta U should equal to 0. And for the second step, we have an adiabatic expansion. So we hit play. So after the gas is finished igniting, the piston still continues to go up, meaning the volume is still increasing, meaning that even during this adiabatic expansion, Q is of course equal to 0, but we still have a negative work. For the third step, now the gas that was inside is being released. Okay, any sort of waste is being released, QC. And during this portion over here, we have compression, meaning that it's going to be positive work. And because it is still an isothermal compression, that means delta T is equal to 0, so delta U is equal to 0 as well. So over here, I know it says negative work, but it really should be positive 5.37 joules. And of course, for the final step, we have an adiabatic compression. So meaning that there's no more heat loss. And for this portion over here is adiabatic. So Q equals 0, but we still end up with positive work. Okay, so this is something that needs to be memorized. And overall, we have our 4 steps for our Carnot cycle. Okay. Now, assuming that everything is ideal, okay? That means that the temperature is directly related to the heat transfer itself. So rather than the efficiency based on the amount of heat energy that was transferred in and the work done, Carnot realized that the maximum efficiency, EC, Carnot efficiency, is equal to TH, hot, minus cold, divided by hot. And of course, the unit for temperature is going to be in Kelvin. But it's most important to recognize that this solves for the maximum possible efficiency for any heat engine. It does not mean 100% efficiency. It just means that if you were to get rid of all the waste, how well could the engine ultimately perform? So Carnot, whenever you see the word maximum possible efficiency, or sometimes they'll use the word ideal efficiency, they're always talking about Carnot and his maximum possible ideal efficiency. So if you talk about humans, for example, right? How efficient are humans in terms of using up the energy? All the food that we intake, how efficient are we in terms of burning those calories and using it to move around, to think, and to do all that we do? It's tough to get a very high efficiency. In fact, humans are only about 30% efficient. That means 30% of the food that we take in gets used for what we do every day. 70% of that is wasted. And this is after millions of years of evolution. But if you were to look at a car, for example, whenever we talk about a gallon of gasoline, how efficient are cars? Well, cars, if you were to actually calculate the efficiency out, will end up being maybe 5 to 10% efficient. And the rest gets wasted as gas that gets exhausted out into the air. Anyway, so if we take a look at an example here. A steam engine operates between 500 degrees Celsius and 270 degrees Celsius. The first thing we should do is convert to Kelvin. So this is 773 Kelvin, and this is 543 Kelvin. So when we talk about the maximum possible efficiency of this engine, you would end up doing 773 minus 543 divided by 773 Kelvin, which equals to 0.298 efficiency. So the maximum possible efficiency of a steam engine would technically be about 30%. But in real life, do we actually see 30%? No, we'll see maybe a third of that at most. So when is an engine most efficient? According to Carnot's formula, when exactly would there be 100% efficiency? Well, if we take a look at Carnot's formula, EC is equal to TH minus TC over TH. How could you possibly create more efficiency? Well, technically, you'd have 100% efficiency when this is 0. If somehow we could actually create absolute 0 Kelvin, and have basically none of the heat discharged, then we would have 100% efficiency. But that's impossible to do because absolute 0 is not a number that we theoretically would be able to produce anyway. However, looking at this formula, there is a way of increasing efficiency, if not to 100%. And the easiest way to increase the efficiency would be to increase the input temperature itself. Let me give you an example. Let's say we had originally 100 Kelvin minus the output temperature was 25 Kelvin divided by 100 Kelvin. In this case, we would have a very high efficiency of already 75%. But let's say we were able to increase that input temperature. Rather than 100, let's say it was 200 Kelvin. Minus 25 Kelvin divided by 200 Kelvin. Now, if you work this out again, you end up with 87.5% efficiency, meaning that the higher the initial temperature, the more efficient the engine is, and the more work you'll get done. And the perfect example of this is from the movie Back to the Future 3, when Marty McFly was stuck in the wild, wild west. If you remember, at the very end of the movie, they needed to get him back to the future, but the car was out of plutonium. So they wanted to use a locomotive to travel up to the speed that was needed. The problem was locomotives couldn't go that fast. So what Dr. Brown did was he created these 3 special logs that burned extra hot. Now the problem is, when he created those logs that burned extra hot, when temperature increases, pressure increases. And when the pressure increases, unfortunately, that caused the actual smokestack to blow apart. So you can see in the movie that, which is technically kind of basic science, unfortunately here, that by increasing the temperature, the train is able to get more energy out of the coal that is burning. And it's able to reach the speed they want to reach in order for the car to go back. Okay. So let's do a couple more practice questions. The highest theoretical limit of a gasoline engine is 30%. Efficiency is equal to 0.3. So the engine exposes gases into the atmosphere, which is a temperature of 27 degrees Celsius. So of course that's going to be Kelvin. That's being expelled. That's going to be the cold temperature, not the hot input temperature. So that's going to be 300 Kelvin. What is the temperature in the cylinder immediately after combustion? So they're asking us, what is TH equal to? Well, EC is equal to TH minus TC over TH. But this is a little bit more difficult because right now we have 2 variables. We have TH twice. So rather than leaving the formula looking like this, let's rewrite this. So basically, TH divided by TH is 1 minus TH over TC. And now it's a formula that we can more easily manipulate. Okay, so we end up with 0.3 equals to 1 minus 300 Kelvin over TH. So that means we end up with 300 Kelvin over TH is equal to 0.7. And if we work it out, TH is then equal to 428.6 Kelvin. Okay. Let's do one more. Actually, I want to do this one. In one cycle, a heat engine absorbs 500 joules from a high temperature reservoir. So, QH is equal to 500 joules. QC is equal to 300 joules. They say the efficiency of this engine is equal to the 60% of the efficiency of a Carnot engine. Okay. So, from this information here, I can immediately determine the actual efficiency of the engine to be QH minus QC over QH, which is equal to 0.4. But they said that this is equal to 60% of the Carnot efficiency. So that means this is equal to 0.6 EC. So the actual Carnot efficiency, itself, right, the maximum possible efficiency would equal to 0.67. They ask us, what is the ratio of the low temperature to the high temperature? In other words, what's TL divided by TH equal to? So if EC is equal to 1 minus TL over TH, or hot, cold over hot, then we end up with 0.67 equals to 1 minus TL over TH. So the ratio itself would equal to 0.33. Okay? And that's one way of combining the efficiency formula, the actual efficiency formula, with Carnot efficiency.